here we did finish talking about, I would say, a point charge, and now here we are talking about electric potential and field of a charged conductor. Then it's like this one, it has, I will say, dimensions. Okay, then it's not just a point. And here we have a solid conducting sphere. And if you remember from, when we are talking about the electric field, we said that the electric field inside the sphere is zero everywhere because the charges, once you add charge to a conducting thing, the charges, they're going to start repelling each other till they have the maximum distance between them. And this is when we are going to have all the charge actually sitting at the surface. Then if we wish to here graph the relationship between E and R inside the electric field is zero, and then outside E is going to vary as 1 over R squared. And therefore, this is the graph that we can get for, I would say, electric field of a conducting sphere. On the other hand, if we will look at the potential is going to be the same. It's an we call it equipotential surface. Then the potential at any point inside the sphere and on the surface of the sphere is going to be the same. V, which is 1 over 4 pi epsilon 0 q over r, uppercase R, where R, it is the radius of the sphere. Once you are outside, it's going to vary as 1 over R, not as 1 over R squared. Okay, and that is really the graph here showing the relationship between V and R. Now here, just one of the application at the electric field magnitude of about 310 to the 6. This one, 10 to the 6 volts per meter or greater, air molecules will ionize. Ionize means they're going to split. They're going to split to positive and negative charges. And the air becomes a conductor. All right, for a charged conducting sphere, V surface equals E surface times R, which is, this is, I will say, the equation V equals, we use usually D. Thus, if E times M is if EM is the electric field magnitude at which air becomes conductive, okay, we call this the electric strength of air, then the maximum potential Vm maximum is gonna be to which the spherical conductor can be raised is V maximum equals R times E maximum. And now we will apply this to one of the problems that we are going to talk about. Now, if I have oppositely charged parallel plates, like the one we introduced, then here I have positive and negative. And I will say the positives, of course, should be here, and the negatives should be here. The potential at any height y between the two largely oppositely charged parallel is V equals E times y. Okay, it's again, I like maybe to use always E times D. Now, equipotential surfaces mean that I will draw lines where I'm going to have the potential the same, and then I'm going to connect the lines. And when we have the electric field lines, we can draw equipotential surfaces that they are going to be perpendicular to the electric field lines. Then you're going to come here at the same point. You're going to say this is where the perpendicular, 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 and these. And we will, of course, do also one of the labs is going to be about these. And then I will say if we have a positive or negative charge, the equipotential surfaces, they are going to be surfaces, not lines, that they are really perpendicular to the electric field lines. Here, also drawing the equipotential surfaces and field lines for a dipole. Also, we'll do this in the lab. And again, we will choose a point from at a distance r from the charge, and then we are going to draw a perpendicular and then connect the points. Also here two equal positive charges. These here, a dipole means negative and positive, here positive and positive. And like it's the same idea for all. Anytime you have the electric field lines, you will actually draw the equipotential surfaces that they are going to be perpendicular to the electric field. Remember we said also before that the electric field just outside the conductor is always perpendicular to the surface. Like here, if you look at these here, and then we can draw the equipotential. Now, equipotentials and conductors, if the electric field had a tangential component at the surface of a conductor, which is of course not, a net amount of work would be done on a test charge by moving it around a loop as shown here, which is impossible because the electric field is a conservative force. Therefore, again, this is another proof that I will say outside the conductor, at the surface of the conductor, the electric field only had a component which is going to be the perpendicular. Now, potential gradient. The components of electric field can be found by taking partial derivatives of the electric potential. Then Ex is going to be the partial derivative of V with respect to the X. And remember, they have a negative sign between them. And Ey is going to be negative the partial V divided by partial Y. And the same for Ez. And we can say that the electric field is the negative gradient of the potential. All right, now I will introduce some of the problems here that we have for this chapter. For example, here I have a point charge Q1 equal 2.4 microcoulomb is held stationary at the origin. This is my origin here. And a second point charge, Q2, which has a negative 4.3, moves from point X equals 0.150 and 0 to a point that is 0.25. I'm writing here my coordinates in this notation. How much work is done by the electric force on Q2? Work done, it is the charge times V1 minus V2. And then when the charge is negative, you're going to put the negative here. And that is KQ over R1 divided by KQ over R1 minus KQ over R2. I plugged in my numbers and then I found negative 0.356. Just one thing here I want to add, which is when you want to calculate these here, R1 and R2, this is my R1, and R, it is always square root of X squared plus Y squared. This one, it doesn't have a Y component, therefore it's going to be just the X which was 0.15 0 meters. Okay, here I wrote something wrong. This is 0.150. Okay, and for this one here, this is the R. Okay, this is R2, and then R2 also is gonna be x2 squared plus y2, and that is how I calculated this 0.356. Checkpoint 2. This is 3 equal 1.20 microcoulomb point charges are placed at the corners of equilateral a triangle with sides 0.4. Equilateral means like all the sides are equal. What is the potential energy of the system? Take as zero the potential energy of the three charges when they are infinitely far apart. Remember here, U can be calculated as K Q0 over R, and therefore here, since the charges are really equal, we're gonna take the first the potential energy of charges 1 and 2, and then 1 and 3, and also 2 and 3. Then anytime you have charges, you need to include all the effects on each other. Then since they are all equal, each of these is KQ times Q over R. Then you are going to add, and then it's going to be 3KQ squared over R. And that is 0.0971 joules. Now here, we have point charge Q1, which is plus 2 microcoulomb, and a point charge Q2, which is negative 2 microcoulomb, are placed at the adjacent corners of a square for which the length of each side is 3 centimeters. Remember, you need to convert into meters. Point A is at the center of the square, and point B are point B is at the empty corner closest to Q2. Take the electric potential to be zero at a distance far from both charges. What is the electric potential at point A due to Q1 and Q2? Okay, first I'm going to consider point A, which is this one here. And UA is going to be due to both charges. Then it's going to be K Q1 over R1 plus K times Q2 over R2. And since the charges are equal in magnitude but opposite in direction, and they are at the same distance from the, I would say, the point, then they're gonna have equal potentials but opposite in signs, and therefore it's gonna be resultant to zero. Here, how I did calculate that 2.21, I can calculate the diagonal because here this one is 3 and this one is 3, and A, of course, it is at a mid distance between the two. Then you divide by 2. Now at point P, now that is really the distance is going to be different, and I have calculated here RB1 is 0.0424 meters, which is the whole diagonal, and for that one it's the side, which is the 3 centimeters, and then just it's kind of a very easy calculation where this is K and this is plus 2 10 to the negative 6, you need to convert your microcoulombs into coulombs and distances into meters. Now, the last part here, asking a point charge Q3 negative 5 moves from point A to point B. How much work is done on Q3 by the electric forces exerted by Q1 and Q2? Is this work positive or negative? Of course, it's going to be the Q times VA minus VB, and the charge is negative, and we will have, of course, the work done is going to be negative. I feel this chapter, you're going to feel it like much easier than the others, because the other two chapters, because it is talking about scalars. Checkpoint 4, a thin spherical shell with radius R1 equals 3 centimeters is concentric with a larger thin spherical shell with radius R2 equals 5 centimeter. Concentric means they have the same center. Okay, both shells are made of insulating materials. The smaller shell has a charge Q1 equals 6 nanocoulombs distributed uniformly over its surface, and the larger shell has a charge Q2 negative 9 nanocoulombs distributed uniformly over its surface. Take the electric potential to be 0 at an infinite distance from the both shells. What is the electric potential due to the two shells at the following distances from their common center? R equals 0, R equals 4 centimeters, R equals 6 centimeters. Now, the rule here, and of course I did draw the shells, and the rule here, it is the potential at any point is the scalar sum of the two potentials. Now, one thing that you need to know, if the point, it is at a distance less than the radius or equal to the radius, then V is going to be KQ over R. If it is at a distance outside the sphere, then it's going to be V equals KQ over R for R greater than R. And this is the rule. When we are going first to consider at the center, for both spheres, this is inside them. Therefore, V is going to be K Q1 over R1, which is the radius, plus Q2 over R2. And therefore, of course, here with potential, with electric force and electric field, we did not use the sign for the charge. Here we should use it. And then we have, this is at 180 volts. When we are talking about 4 centimeters, 4 centimeters is going to come to be somewhere here. And that actually, it is for sphere number, the inner sphere, it is outside the sphere. For sphere number 2, it is inside the sphere. And therefore, for the smaller one, you're going to get Q1 over R, lowercase r, and for that one, it's going to Q over R. This one here is going to be the distance that is given here, which is the 4. This is uppercase R, is going to be the radius of the second one. And then you're going to add, and we have the voltage as negative 270. Now, the last one, it is R equals 6 centimeters. And of course, now this is really outside both, and therefore lowercase r, and therefore I'm going to have 6 and 6 here, which is the distance. I will not use the radii. Part B, what is the magnitude of the potential difference between the surfaces of the two shells? What is the magnitude of the potential difference between the surfaces of the two shells? Which shell is at a higher potential, the inner shell or the outer shell? Now we need now to put ourselves at the surface of one of them. which is R equals the first radius, which is 3 centimeters, and it is inside shell 2, but it is on the surface of shell 1. Therefore, we are going to have that V1Q, that the same like we calculated before, 180. Now at the surface of shell 2, this is at 5 centimeter. It is outside the inner one, but it is on the surface of the second one. Therefore, we are going to use the 5 centimeter for the first one, and also, it's going to be the 5 centimeters for R2. Okay, and therefore we did calculate V2 as negative 539, and then delta V, it is V1 minus V2, which is 719 volts, and therefore the inner is at the higher potential. This is checkpoint 5. It is very similar to this one, therefore I did not solve. I will leave it for you to practice. Thank you and have a great day, and see you soon in chapter 24.